I'm going to present to you a little bit about QuEST, which is this simulator of quantum computers you may have heard. But I'm actually also going to contextualize what QuEST is and what strong full-state simulation is. So in fact, the majority of this talk will really be about classical simulation of quantum computers in a generic sense. So with that new context, this talk is really entitled The Quest for Classical High-Performance, Full-State, Strong Simulation of Digital Error-Prone Quantum Computers. And we'll learn what some of those phrases mean as we go along. I just want to disclaim everything expressed here are my own views. They don't represent my employers or anybody else mentioned. Okay, so here's the table of contents. What is simulation? What does that phrase mean? Why would we choose to simulate quantum computers? Don't we have them? How simulate quantum computers? What are the mathematical frameworks by which we can emulate a quantum computer? And then I'll introduce this dichotomy you may have encountered, strong versus weak, and then what a full-state simulator is, the kind that QuEST is. Then I'll discuss what is QuEST. How does QuEST fit into that context, that painting I just described? Who is developing QuEST? What's going on with it? And what are they developing? What are the new features coming? What are the old features? What is simulation? I asked Google, and it gave a pretty illustrative definition at the bottom. It says, simulation is the reduction of a computer model of something, especially for the purpose of study. I gave ChatGPT the same question, and it gave an excellent answer. It describes how we extract the key characteristics of a system when we model it. The model is then manipulated or observed under different conditions to understand how the real system might behave under similar circumstances. This is fantastic. This is a very practical, explicit definition of simulation. We're going to be studying something as we change something, as we change the conditions. Here's a very explicit instantiation of what simulation is. You have a bunch of equations, say analytic equations that comes from your theory, maybe from your science, and you instantiate those numerically on a classical computer. Maybe you're making an approximation, maybe you're solving things exactly. In any case, you're outsourcing what would be your analytic labor to the machine. And you yield either eigenstates or dynamics or some output observable that humans are very interested in. This example is a three-body problem, which was a little pop cultural reference for every one of my colleagues who seem to be talking about this and stuff. Why would we simulate quantum computers? Okay, maybe I've argued the merit of simulation generically, but why quantum computers? Don't we have those? Well, every developer of quantum algorithms has experienced this scenario. You write a new quantum algorithm, you're very excited, you submit it to a journal, and reviewer number 2 tells you to run it on a quantum computer. If it's so good, why don't you execute it? We have quantum hardware today, don't we? Why don't you run your algorithm? Well, of course, you can't, because today's quantum prototypes are mint prototypes, and they're crap. They're not the target application of your algorithm. They're noisy, constrained, they make mistakes, they restrict your topology or your gate set in ways that may be catastrophic or incompatible to your algorithm. So if you do this, you take your quantum algorithm and run it on hardware, usually you get noise out, or something uninterpretable to the success of your algorithm. What you really need is something adjustable. Something where you can, say, change the parameters of the hardware until it proves compatible with your algorithm. And the only way to really get tunable hardware is to simulate it. It's very hard to build 10 million instances of the same kind. Okay, so I've described a very rudimentary application of a simulator in order to dichotomously test, does my algorithm pass or fail if I actually ran it on quantum hardware? But that's one of many, many reasons to use simulators. Some more reasons include to change archetypal, architectural, or topological features of the hardware that you can't do in reality. Maybe you wish to run your algorithm and test its resource costs when you have limited qubit connectivity. We can't go and build a quantum computer physically for every configuration we wish to test. So you simulate the variations of the hardware, just like the ChatGPT definition. It describes varying conditions, something only possible in simulation. Or you may wish to motivate quantum supremacy and advantage thresholds. So i.e. motivate precisely how many qubits at what fidelity do we need to beat a classical computer. Well, that's half a task for classical computers to set that threshold, right? So there's another application of simulators. Actually evaluating error correction thresholds. So precisely calculating what do I need to tell the experimentalist and with them to achieve in order to have logical qubits. That's a quantity that we can ascertain with simulation. Even to produce quantum circuits, which I'm not really sure how that's visualized by this block, but even creating quantum circuits to dispatch on a quantum computer, we often use classical simulators to produce, or at least we can use. For instance, we're performing an approximate recompilation to target a different gate set. We even now see people using classical simulators just to profile their classical hardware. So they have some shiny new classical supercomputer, they really wish to stress test it, or generate a lot of heat. Throwing a simulation of a quantum computer at it is a great stress test. It involves huge amounts of flops and memory movement. But the most important and most compelling application
is to rebuke claims of experimental progress. So yeah, you might have noticed there's this game of cat and mouse between the classical community and the quantum community, where we devise new, bespoke, specialized simulators to simulate faster than quantum means precisely the circuits being nominated for quantum advantage and supremacy. So that's a lot of fun. So hopefully now I've established good motivation for why we should use simulators for your next journal review. There are two categories of simulation of quantum computers that have emerged in the literature, which are the strong simulators and the weak simulators. This is not an evaluation of their power or potency, even though I'm now going to use a bunch of provocative graphics that suggest so. These really refer to the types of outputs you can get out from them. The strong simulators, they maintain expensive, dense, but very detailed descriptions of the simulated quantum state. For example, you might track, the echo's back, you might track every individual amplitude associated with every unique classical configuration of your system, which we know grows exponentially with the number of partitions of the system. It's very expensive. You're paying this huge memory upfront, but it's very powerful in that you can answer lots of questions. So you can do your simulation, and thereafter, you're very free to ask questions about the output state. E.g., what's the expectation value of this operator? Or what's the probability of this measurement? Or how much entanglement is there between these partitions, etc. Weak simulation, on the other hand, involves propagating a subset of the full quantum information. You throw away the tracking of information that isn't used in the calculation of your specific output. So often you're embedding the question you wish to answer in your initial state. And you're propagating only the information or that which approximately contributes non-negligibly to your answer. This means you're much more limited in the questions you can answer at the end of your simulation. So you can still often get expectation values, which is often all we want. For instance, if your goal is to emulate a quantum computer, that is, get precisely the outputs that a real computer would output, and you don't care about any of the maths or the artifacts of the simulated physical formalism, then you might use a weak simulator. But why? Why would you use a weak simulator over a strong simulator? There is a trade-off, and that is resource costs. So weak simulators, by throwing away the information that you don't need to answer your final question, weak simulators have way smaller resource overheads. So for instance, often you can avoid the exponentially growing initial memory costs. They might grow later unless you make certain approximations and tune hyperparameters, but you can at least start a simulation of a system that is intractable for a strong simulator. You can also use approximations more easily, I'll say, as in there are sort of more tricks that you can deploy during simulation to keep your resource costs small. And it's sort of easy to quantify what that's doing to your accuracy during simulation. Whereas strong simulation, there are methods to keep costs low, but much harder to grapple with. So it means in this example, if you were asked to simulate a 100-qubit weakly entangled circuit, that's child's play for some simulators, like the Pauli transfer matrix simulation with truncations. But for a strong simulator, it would crap the bed. There is no way you're getting 2 to the 100 amplitudes represented. So, full state simulation, still very useful. Still pretty cool. One example of a full state simulator, strong simulator, I should say. One example of a strong simulator is the full state simulator, which I've been hinting at with my graphics so far. This is also referred to as the state vector formalism, or affectionately as the brute force simulator. And it involves, as I've alluded to, storing an amplitude for every possible unique classical configuration. So e.g. 2 to the n complex scalars, where each complex scalar is an amplitude. Operations upon the state are then logically very simple. They're usually just linear combinations of these complex numbers. But if you'd like to find out how and what kinds of operations those are and what this graphic means, you'll have to come to my afternoon session, which I think is called QuEST Architecture. Architecture of Core QuEST, parallel session 2A, where I'll talk more about the algorithms behind the new flavor of QuEST. So what are the benefits of strong simulation or full state simulation? Why is QuEST full state? Well, there's a few. Okay, it's strong. So you can answer any question posteriori. Pay your expensive simulation. Ooh, it's really going to limit your qubit number. But once you've paid that cost, you can get any question answered, get any information out of it thereafter. The maths is simple. Even I can understand it. So the mathematics of tracking, what we should do to the state that we're simulating are very similar to the mathematics of quantum information theory, where we're just manipulating kets and basis states. Why is this good? Makes bugs slightly harder to implement, although I'm pretty good at creating them. And it also makes extension and custom integration easier. You can look at the code of QuEST and be like, oh, I get it. I see. This is an amplitude moving around. The state is familiar, as I guess I just said. You can peek at it during simulation and go, what are all these numbers? Oh, that's the state vector. I know state vector. So there's no parsing or conversion needed if you wish to get the state out. That's exactly what we're tracking, the state. It's very easy to parallelize. So this simulation really boils down to a huge number of floating point operations. Very, very simple. There's just lots of them. And so that means we can throw the last 2 decades of high-performance computing progress at the problem. So integrating GPU acceleration or multi-threading or distribution, trivial. Well, not too trivial. I don't want to lose my job, but it's easy enough. And why hardware is good because machine learning, whatever. The costs are very predictable. So if you ever played with a weak simulator, you know that in order to actually get a sufficiently accurate output while keeping your resource costs low, there are lots of parameters to tune. E.g., it might be thresholds where, above this certain threshold, destroy things of a certain size. These hyperparameters can be sort of quasi-analytically motivated in advance, but often they have to just be run, and then you find, my resources blew up. Now I have to redo it with a changed hyperparameter. In the full state picture, we have no hyperparameters, except the floating point precision, which you'd only ever change if you were really squeezing out performance. So you just throw your generic circuit straight at the simulator. Is that my next point? Oh, that was my next point. No hyperparameters. Anyway, if your circuit can fit in memory, e.g. it's 30 or less than 45 qubits, you can just throw it at a state vector simulator. Whereas if you wish to use a weak simulator, you have to study, is my circuit a member of the family of circuits that this particular simulator is efficient at simulating? And finally, we can play God. We can look at the quantum state at any intermediate stage. We have the dense quantum state representation. So you can stop after the first gate and be like, let me pause the simulation. What are the amplitudes like? You have all that information there. So it's very useful. And for these reasons, full state simulators are a prudent first choice of simulator. So don't use a specialized weak simulator if you don't yet know you have to. If you're simulating 25 qubits and you don't know how much entanglement your circuit's going to generate, you don't know all these funky internal quantum properties, throw it at a full state simulator. Only when that proves inefficient should you then think, is there a bespoke, specialized simulator that can get me to the regime I want? So baby's first quantum simulator is the state vector picture. So that finally brings us to QuEST, the Quantum Exact Simulator Toolkit. What is it? Well, it's an exact simulator, and by exact I mean full state. So we don't make any approximations. We're just faithfully tracking as much quantum information as is necessary to get the complete picture. The S stands for strong. It's a strong simulator, so you can pause simulation at any time, peek at the state, answer any questions posteriori, etc. And the toolkit is just because we're really uncreative in creating suffixes. And the name QuEST, it's a nod to Sir Galahad's quest for the Holy Grail, which you can see embedded in the logo, which is Simon Benjamin's masterstroke. See the Greek sigh in there? Very cool, very clever. Okay, who's working on QuEST? What's the current status of development? So active development right now is primarily by the University of Oxford, the University of Edinburgh, the National Quantum Computing Centre, and Quantum Motion, and some help from NVIDIA. Worth acknowledging previous contributions by AMD and HQS, and previous financial support from the Clarendon Scholarship of Oxford, the Quantum Computing and Simulation Hub, and the Networked Quantum Information Technologies. I've never read that acronym out loud. Okay, what's QuEST doing? What's the deal? QuEST's founding philosophy was write once, run anywhere. So you probably have had the experience of writing a quantum algorithm, simulating it up to 4 qubits, and the reviewer says, run it bigger. And you go, oh, I was doing it analytically. I can't run it on 10 qubits. So the aim was to write a simulator with an interface which is constant between deployment platforms, which is agnostic. So that when the reviewer inevitably asks you to scale to 25 qubits, then you can just deploy to GPU, and the code doesn't change. Or when they say, nope, make it 42 qubits, you deploy to the cluster. No changing the code. So that was the founding philosophy. So these are all supported hardware backends. What's been going on recently? Recently since like August 2023. We got a QQuantum backend integration. So you may have heard of NVIDIA's QQuantum backend, which is like this low-level GPU framework for simulating state vectors and soon density matrices. It's pretty cool. We now have integration with that, so it's probably a lot faster than the custom bespoke GPU kernels that we originally wrote QuEST with. Although I never benchmarked it, so if you wish to compare, the code's waiting for you. Windows support, yay, we have native Windows support. So even cursed Windows users can enjoy the fun. AMD GPU support, thanks to a contributor from AMD. So you can now deploy QuEST straight to AMD GPUs, just like you do the NVIDIA GPUs. Nothing is changing in your code. Support for OpenMP5, yay! So now if you're using like GCC 10 and above, QuEST will actually run now. You don't have to turn off multi-threading. Okay, what are the upcoming features? Some exciting stuff is in the space. Here is QuEST's existing deployment if you might use a GPU. Maybe soon you can use multiple GPUs. Maybe those can be tightly connected. Wow, what does that mean? You've got your cluster. Everyone has access to a university cluster. Whoa, what if they had GPUs? And something very exciting, heterogeneous deployment. You've got a whole big lump of hardware sitting there. You've got multi-core CPUs. You've got maybe a bunch of GPUs connected. Maybe even have multiple nodes. You can use them all. You can throw them all at QuEST now. Auto deployment. I couldn't generate fancy graphics for these. We now have a facility for runtime choosing of these backends. You might not know whether, is my qubit the right, my quantum register the right size to make good use of multi-threading? I don't know. We'll choose for you. Just instantiate it and we'll do the magic. The build system will be significantly cleaner. I don't know if you've tried to grapple with QuEST C make and GNU make builds before. It's pretty awful. A brand new QuEST re-architecture. So the code is now significantly cleaner, less full of boilerplate and code duplication, making external contribution much, much easier. Integration with external libraries will be much easier. As I said, yeah. And newer algorithms. So a bunch of the core QuEST functions will now run faster using polynomially accelerated algorithms, which is pretty exciting. I said polynomial, I didn't say exponential, so this is still worse than having a quantum computer one day. But you might notice, my multi-qubit unitary is now 10 times faster. How the hell did that happen? It's going to be this little secret sauce. And finally, if you're working on QuEST, let us know. We can collaborate. We can make sure we're not duplicating efforts. So we're going to make a roadmap or some sort of system to say, hey, I'm working on this, and I'd love to pull to the open source repo. We don't have that yet, but if you're interested in it, even setting that up or contributing code, then email me at tysonjones.input@gmail.com. Okay, thanks very much.